The next topic is how the executor service can be implemented. There's a number of ways to implement it. We're going to talk about one of the ways now, and that way is through a class called the ThreadPoolExecutor. And this is a very, very interesting class. As you can see just by a quick glance through a subset of its methods, it's got quite a surface area in terms of capabilities it provides to clients or to users of this class. And we're also going to talk about how to customize the behavior of the ThreadPoolExecutor based on parameters that are passed when an instance is constructed. And this is really, really cool. So what is a ThreadPoolExecutor? Well, it's a class. It's actually a class that you can make an instance of. And it implements the executor service interface indirectly via the abstract executor service superclass. So executor service is an interface. There's an abstract superclass called abstract executor service that fills in a bunch of the methods that are defined in executor service. And then the ThreadPoolExecutor inherits those common methods and does a bunch more stuff. The ThreadPoolExecutor runs each submitted task, each task that's given to it by a client, using a worker thread that's provided by a pool. There's typically a pool of worker threads. Here's a little cartoon that demonstrates kind of what things look like. So you can see here, here's the ThreadPoolExecutor instance. We have a bunch of worker threads that are running, and there's a way for a client to submit a callable to the instance of the ThreadPoolExecutor. And when the submit method is called, that callable is stuck on a queue of pending tasks, and that's called the work queue. And the worker threads in the pool basically spend their existence, for the most part, waiting for something to do, like hungry puppies, something to chomp, to eat, to chew. And when a thread becomes available, it goes and grabs the next item from the queue and runs it, and then that will compute the task asynchronously with respect to the caller. And this queue here is what's called a blocking queue. So if the queue is empty, then the threads will just wait for something to show up in that queue. The queue is actually an unbounded blocking queue, so it has no restriction on how big it can be. But you can change that by parameters you pass in, as we'll see here. The constructor can be configured using a whole slew of different parameters. Here's what they are. So the first two parameters here control the number of threads to keep in the pool, even if they're not currently being used, even if they're, quote, idle. That's the core pool size. And then there's also another parameter called max pool size, which is the maximum number of threads to allow in the pool. And we'll see here that different types of thread pools have different settings for these parameters, or given different settings, given different values for the parameters to control the behavior of the ThreadPoolExecutor. There's also some other parameters that keep track of the lifetime of threads in the pool. So this is called the keep alive time, and this is the maximum time that excess idle threads will wait for new tasks before terminating when the number of threads is greater than the core. So let's say, for sake of argument, that the core pool size was 4, but the max pool size was 8. So what would happen as things grew and got closer to 8, then the keep alive time says, if some of those threads aren't used by more than a minute, or whatever it is, 30 seconds, an hour, whatever your keep alive time is, and whatever the time unit you want to be, then in that case, terminate those threads back to the core pool size. So if you had 8 threads, but the core pool size was 4, then and let's say you were saying up to a minute, if a thread is idle for up to a minute, shut that thread down if there's more than 4 of them to keep it at 4. So that's the idea here. And the time unit is basically either milliseconds, microseconds, or seconds. So that's how to interpret what the keep alive time value's time unit is. The next parameter here is the work queue, and this is the queue to use for holding tasks before they're run. And there's a bunch of different queues that you can have. One is to have direct handoff, and direct handoff is what's used by the cached pool. So there really isn't a queue at all, it's just basically a synchronization point. And this is implemented by something called a synchronous queue. And this implements a model called rendezvous, where the caller blocks until a task is handed off to a new thread or a cached thread. The good thing about The direct handoff approach is it avoids deadlock on any internal dependencies because you're always creating a new thread. There's always a thread that's being created. The downside is if you have lots of requests, lots of tasks that come in at any given point in time, you can create a heck of a lot of threads, which is kind of defeating the purpose of why you want to use a thread pool. Another model, which is probably the most popular one, is to use unbounded cues. And this is what's used by the default fixed thread pool, fixed size thread pool. And the good news there is, as with almost anything, whether it be in the router layer or the operating system layer, using queues and unbounded queues is very helpful for smoothing bursty requests. So if you have a lot of requests that show up at one point, then using a queue is good because it'll kind of deal with the surge gracefully. The downside is, as you might imagine, because it's an unbounded queue, it can consume an unlimited number of resources. So you can eventually run out of memory if you're not careful. The third model, which is used if you make your own custom fixed size thread pool, is to use a bounded queue. And as the name suggests, there's a limit to the number of things you can put on there. So the nice part is it limits the utilization of resources, which is good. So you're not going to run out of memory. The downside is trying to figure out what the actual number of elements to allow in the bounded queue is hard to tune. Like, what should it be? It's either going to be too big or too small, undoubtedly. And you can end up with deadlock on yourself. And if you want to learn more about how and why to do that, this is a good link to look at to see how thread pools with fixed size queues or bounded queues can induce deadlock. The final parameter here is the thread factory. And this is an object that has a factory method that's used to create threads. And you can dictate what kind of thread to make. So why is this useful? Well, using a thread factory means that we don't have to hardwire the calls of creating a new thread. And therefore, you can have special threads. You can have special priorities, special names, all kinds of things can be handled by the thread factory. We'll show some examples of this. There's a default thread factory that is used, which just creates a thread without anything special. It's just the normal priority, it's just the normal name, and so on. But if you want to take control of those things, you can make your own thread factory and pass it in. So that's the end of the overview of the Java ThreadPoolExecutor. You rarely use this particular class directly, but you can. If you want to make your own custom thread pools, you can create your own factory method that sets those parameters to whatever you think is important, and then you can have your own custom thread pool executor. You could also go so far to make your own thread pools altogether, and there are other examples of thread pools beyond the thread pool executor. For example, the work stealing thread pools we talked about, or fork join pools are good examples of that. But the good news is there's plenty of things to reuse, there's plenty of things to customize out of the box, and there's room for further customization if you so desire.